right, so let's get into what these intermolecular forces are. There's three types of them. The first and the weakest intermolecular force, remember these attractive forces. So when you think of intermolecular force, and we discussed it in the last lecture, but I want you to think of the stickiness. All right, this is the stickiness. It makes these molecules stick together, okay? It is an attractive force. So the stronger the attractive force, the closer the molecules are going to be, or particles are going to be, to one another. There are three types. The first one is called the London dispersion force. It is the weakest out of the intermolecular forces, out of the attractive forces. The London dispersion force, and we're going to talk about it more when we get into chemical bonding. But what it is you need to think of an atom as the center has this nucleus, which is positively charged, okay? And you have surrounding it these negatively charged electrons. So these little dots right here are your negative charges, and they're just kind of floating around the nucleus and moving around. And they're going to equal the charge of the nucleus, all right? So this would be a +3 charge, all right? So it balances out. Okay, and so when it balances it out, there's no overall charge on the particle. Okay, it's neutral, right? Because +3 with 3 minus is going to equal 0, right? So it's a neutral charge. Well, what the London dispersion force is at any given time, it's an instantaneous force. So it happens just instantaneously for a split second, and then it goes away. But what happens is these electrons don't move in unison, right? So they're not moving they're not orbiting the nucleus like the planets orbit the sun. They're roaming around in random patterns at random velocities. And at one point in time, it's a probability that you'll have more electrons gathered on one side of the atom than on the other. And this is going to create something called a partial charge, a quick instantaneous charge where one side of the particle or molecule will be positive and the other side of the atom will be negative. And this instantaneous charge on the particle will create an instantaneous attraction. And we call this the London dispersion force. Now, the London dispersion force becomes stronger as you create more electrons in bigger molecules or in bigger atoms. It's not very strong in smaller atoms or smaller molecules because there's not a whole lot of electrons in that compound or in that particle. So it's really only an important force in a molecular particle when there's a whole lot of electrons. But it's instantaneous. It happens for a split second and then it goes away. All right, so that is the London dispersion force. Sometimes you'll also see it called the van der Waals force. The second type of force is called a dipole force. A dipole force is an attraction between partial charges, but this is a constant partial charge, and we're going to talk about what makes something have these partial charges when we get into chemical bonding, but they're called polar. They are polar bonds or polar molecules. And these type of molecules or particles have these partial charges all the time. So it's not instantaneous like in the London dispersion. This is something that is a constant charge on the particle. And we'll talk about all that later on. But just know that molecules that are polar, that have these charges all the time, are dipole forces. So they attract to each other. So wherever a partial positive is, it's going to be attracted to a molecule with a partial negative. And that's what you see these red lines here. These are the attractive forces, and you can always see they're attracted to the opposite charge. So this right here is a dipole force, and it's going to bring those two molecules closer together, okay, make them stick to each other, okay? Think of it kind of like glue. All right, and the third type, which is the strongest out of all three of them, is hydrogen bonding. Hydrogen bonding you've heard of when you were talking about DNA, because the hydrogen bond is what helps make the DNA structure. But hydrogen bonding is shown in molecules that have hydrogens directly attached to either an oxygen, a nitrogen, or a fluorine atom. Okay, so when hydrogen is directly attached to, you can see here, It's directly attached to an oxygen. All right, it has hydrogen bonding capabilities. So it will be attracted to another molecule that has hydrogen directly bonded to a nitrogen or a fluorine or another oxygen. And so this right here is hydrogen bonding. It's not a real bond. All right, it's just an attractive force like the polar force or the London dispersion force. But it is the strongest attraction out of all three. If a molecule or a particle has all three of these forces, they are going to have a very, very strong attractive force, and it's going to give them very high melting points. Okay, it's gonna take a lot of energy to get these types of substances to melt from a solid to a liquid, or it's going to be very hard to get them to boil. So if they have all three of these forces, they are going to have very high melting and boiling points. So it's going to take a lot of energy to get them to go into a phase change. So that's why it's so important, because the energy has to overcome all of those attractive forces to get them to separate, to get the molecules or the particles from a solid to separate into a liquid, and then to get the liquid particles to separate even further to get a gas. So that's why we talk about intermolecular forces, because they have that stickiness, that attraction to one another. And the energy that we apply in the form of heat have to overcome those forces.